Hello everybody, and welcome to chapter 7 of our nanoelectronics course. Today we're going to have a look at transistors and how they operate. Generally, we should remind ourselves that the transistor is so important in our devices because it can be used either as a signal amplifier, so it is extremely important for analogic applications. Think, a sound amplifier, for example, or it can be used as an on-off switch. So this is particularly important for digital applications. So it is a device that permeates all fields effectively of technology. Any technological device will definitely contain in some way transistors and obviously other components. Now, historically, there have been several types of transistors, but the two main types that we should remind are this one here, the BJT, the bipolar junction transistor, which was all made by a single piece of silicon and doping in different ways. So, and this was effectively made in this way. So, for example, it could be a NPN or PNP and so on. So, that's what a bipolar junction transistor could be. So this is a single piece of silicon doped in one region N, one region P, and one region N again. So effectively, these are two PN junctions connected together. And but the problem with this device is that is quite power hungry. And that's how then the MOSFET was introduced in the early 60s. So the MOSFET, I should remind you, stands for metal oxide semiconductor field effect transistor. So the MOSFET that we will talk about in this chapter is a field effect device. So this already is pointing us to how this operates. So it uses electric fields to operate, and we will see in a moment how. So the MOSFET is, because it's such a low power, is particularly useful for many different types of applications, and also particularly is very useful in digital applications. So we've seen the schematic of a MOSFET at the very beginning of this course. Here we have this schematic again in front of us, a cross-section of a MOSFET device, a typical MOSFET. So we can see that we have source and drain regions that are N-type doped, and then the body, the substrate, is a P-type. And the region in between is the region that we've identified as the channel, where any current will be passing through. And then on top is our gate stack with the metal gate and an oxide in between the metal gate and the silicon substrate, the channel. This is clearly a three-terminal device, source, drain, and gate. Sometimes we may have a contact also on the body of the system, could be generally grounded. But the main idea behind this device is that we can control the current passing through the channel by changing the potential, the bias applied on the gate. So this here is the symbol we use to represent the MOSFET in a circuit. So what we've just said is that effectively the current passing through the channel is controlled by the potential we apply on the gate. So IDS is controlled by VG. So the parameter that we are controlling here is IDS, and the controlling parameter is VG. In the next slides, we will focus on this type of MOSFET for simplicity that has a P substrate. And just to be familiar with the naming that and the formalism we will use, this type of MOSFET is also known as an N-channel MOSFET. So, and we will see why in a moment. But the naming is quite clear. So in this case, we will see that when this device operates, the channel that is created is N-type. Okay, so when we are using a MOSFET that has a P-type substrate and source and drain are N-doped regions, then this means that this is an N-MOSFET. So just to visualize what we just said, the transistor, as the word should suggest us, transistor comes from trans resistor, is a device where is effectively a variable resistor, where this variable resistance is effectively between the source and the drain contact, and this variable resistance is manipulated by applying a certain gate bias on the gate. This device is extremely low power, and the reason it is low power is because between the gate and that is the controlling parameter, the potential applied on the gate, and the controlled parameter, that is the current flowing through the channel area, there is an insulator. So in order to control whatever is happening in the channel, there is no real charge that is being injected from the gate into the system. It is only the effect arising from the application on the voltage bias on the gate that allows us to control the channel. So there is no power consumption effectively in controlling the transistor through the gate. And that's what makes this device extremely low power and so important. And that's also the reason why the MOSFET transistor has effectively replaced in most fields the BJT transistor and is the mainstream element in CMOS technology today. So let us have a look now in detail at how this device operates. So here I have again the schematic of our N-MOSFET. And here on the right hand side I've put a plot that shows which is the output characteristic of this device that in a way summarizes its operation. So we shall try in the next slides to try and explain why this plot of IDS, the current through the channel flowing through the between the drain and the source, versus the voltage applied across the drain source contacts, has the shape that is shown here. So we shall try to understand why this plot looks like that. So in order to do that, let us imagine first of all, that we apply a certain bias positive on the gate contact. Let us say 5 volts. On the drain and source we are applying nothing yet, so we can imagine that they are at 0 volts. So this means that effectively on the MOS stack that sits on top of the transistor is represented basically by this is our MOS stack, or capacitor if you like. There is now a certain electric field, so we have the insulator is polarized as I've shown here, so negative charges at the top, positive charges at the bottom, and so this electric field that is caused by the voltage we have applied on the gate electrode effectively will attract negative charges from within the bulk of the silicon substrate to the interface with the oxide material. Effectively, what we are doing is we are bringing this MOS device, which is made of a metal, an oxide, and a semiconductor here, in inversion. We are attracting minority carriers. This is a piece silicon substrate, and so we are attracting electrons that are minority carriers to the interface. So we are bringing the MOS stack in inversion. And in this situation, these minority carriers should distribute more or less in qualitatively, let us say, in the way that I've shown here, should create a flat region, flat I mean like that, between the source and the drain, and so effectively bridging the drain region and the source region that are also n-type. So we have the drain is n-type, the source is n-type, so they both have a lot of electrons, and now there is a region that is also effectively n-type, because we have created an inversion region there that is bridging these two together. So effectively we could say that now we have created a channel. This source and drain are connected now. But still there is no current passing through, because between the drain and source there is now still no voltage difference applied across them. We only have the electric field due to the gate that has created this inversion situation. And so on this plot we are effectively here. There is zero current in the channel, because the voltage across drain and source is also zero. Let us imagine now, or let me just point out that because the MOS stack, the gate stack, is in inversion, this means that the P substrate is depleted, so the majority carriers have been depleted away far from the channel region, and in between the minority and the majority carriers there is now these immobile charges that are also negative. And remember that these immobile charges are really a lot, because the substrate is a p-type, and so there are really a lot of positive charges. So if the positive charges have been depleted away, then they've left behind a lot of immobile negative charges. So although my drawing here is not showing that, the negative charges that are immobile in this region are really a lot. And if we were able to count in the number of these immobile charges, we could realize that the number of immobile charges is it's a huge number compared to the number of mobile minority carriers that are also negative, that have accumulated at the interface here and have created the channel. So while locally the channel is indeed an n-type effectively, the total amount of this charge, this negative charge that is mobile, is very small compared to the huge amount of immobile charges that are here in the depletion region. Okay, this is just something to keep in mind. We may need it later on. So if we now imagine to apply a small VD bias, and we assume that from this point onward that the source is always at 0 volts, so is at a reference potential 0. So if we now apply 1 volt, now we have that there is now an electric field between the drain and the source contact that is directed in the way that I've shown here. So now we have two electric fields. The electric field that is directed vertically because of the voltage we have applied on the gate, and the horizontal electric field that is rising because of the voltage we applied on the drain. So the total electric field in the channel region is the combination of these two electric fields. But what we qualitatively can say is that for sure now there will be some electrons that will be very happy to move from in the channel from the source toward the drain, more in particular, because of this electric field, horizontal electric field that we've generated. And we should expect that because the channel has the shape we've shown here this could be looked as a piece of material that has a certain resistivity, certain geometry. So this would behave as a normal resistor, if you like. So if the drain bias is relatively small, then we should expect that this system behaves effectively as a resistor. And so we should be moving along effectively a straight line for a little bit. So that's why we are here. So VDS is 1 volt, and we get a certain current, whatever that number is. But the most important thing is that if VD is relatively small, we are moving along a straight line. So this regime is called the linear regime for this reason. So the transistor is effectively behaving as a pure resistor. And because though the total electric field in the channel area is actually the combination of these two electric fields, we should expect that these free carriers that are forming the channel should readjust themselves in terms of their spatial distribution to accommodate to this new electric field that is not just directed vertically, but is now directed in a diagonal way. So if this is the electric field due to the gate, and we have a small, say, electric field due to the drain source bias, then the total electric field is the composition of these two, and so the total would be something like that. And so we see that the C, let's say, the sea of electrons that form the inversion region, the channel of the transistor effectively, modify their spatial arrangement according to the direction of the total electric field. So we should expect that if we keep increasing the horizontal electric field, the total electric field will keep deviating, let's say, from the vertical direction, and so also will do the spatial distribution of these minority carriers in the channel region. This means that if we keep increasing the horizontal electric field, what will happen is that at a certain point the sea of electrons that form the channel will be pushed to one side, effectively struggling the channel at one end. In this situation, what we would say is that the channel is pinched. In this condition, we are in the so-called saturation regime. From this point onward, as soon as the channel becomes pinched, we enter the saturation regime. So we started in this point, we moved, you know, in a roughly straight line, but then the actual curve started to deviate from the straight line until it became effectively flat. And now we are in this point at VDS quite large, in this case 7 volts. We are now here. And so we are now in a situation where the current through the channel will not change anymore. So this is the saturation region. What I've been saying to you here about the charge distribution and so on is still very qualitative. We will come back to charge distributions in a moment later on, when we will have a much closer look into how charge is actually distributed. But for now, for the sake of just understanding the operation of the device, what we've said is qualitatively fine, and we can be happy with this type of approach. Okay, so we've clarified that why the transistor can be considered as a variable resistor controlled by the gate bias, and we've understood why the output characteristic of the transistor has to have the shape that we've seen previously. Is shown by this graph here. So let us now try to quantify a little bit which should be the relation between the 3 parameters we've come across until now, which are IDS, VDS, and VGS. So definitely IDS is clearly a function of both the VDS, the voltage across the drain source region, and the VGS, which is the voltage applied on the gate, as we've said previously. Now, how should we expect this current to depend on the fundamental parameters of our device? So here is our planar MOSFET transistor. The channel is here, the source and drain, and the distance between source and drain is the length of the channel. The width of the channel is represented here, and so on and so forth. So what we should expect, for example, is that if W, the width of the channel, is increased, the current flowing between the source and the drain should also increase, because obviously we are increasing the chances of some charges to flow from the source to the drain. And so we should expect that the IDS should be proportional to W. So W should appear at the numerator of whichever formula is that. So regarding L, what we should expect is that if L increases, we are making it harder for charges to move from the source to the drain. And so we should expect that L should probably be at the denominator of this formula that we are building up. Another thing that we should expect is, for example, that the mobility is also the numerator. The mobility, as we've said, quantifies how easy it is for charges to move into in our semiconductor in response to a certain electric field we have applied into that material. So we should expect that the larger is the mobility, the larger will also be the current flowing through this device. And lastly, we should also expect that the capacitance of the gate stack COX of the oxide should be at the numerator. And the reason is that, as we've said previously, the transistor is a field effect device, and so it is the capacitance of the gate stack that is effectively driving the device itself. As we've explained previously, the charge in the channel is the charge that is effectively induced by the electric field in the gate stack. And so by recalling that the charge in the channel is COX time Vg, we can clearly and quickly realize the fact that the larger is for every given value of Vg, the larger is the capacitance of the gate stack, the larger will be the charge in the channel, and so the better will behave, the more current will be able to deliver our transistor. And so that's why we should expect that COX should be at the numerator. And then there should be some function of both the voltage between the drain, the source, and the voltage between the gate and the source. And so in the next few slides, we will try to analyze in more detail how in practice this IDS function should be. Please note that the COX with this tilde symbol on top excuse me, indicates the gate capacitance per unit area. So also this charge here is the charge per unit area. And here I've just reminded you about which is the relation between mobility and the drift velocity and the electric field. Now, from what we've seen until now, the transistor is a device that only when the gate voltage has a certain value, the MOS stack goes into inversion, and so the transistor is able to conduct current through the channel. Otherwise, the transistor is not able to conduct current through the channel. So this means that there must be a threshold voltage that separates the situation where the transistor is on from the transistor is off. Where on and off, we mean the transistor can pass current through the channel or can not pass current through the channel. And for the specific case that we've seen here of an N-channel MOSFET, these two regions are represented by those gate values that are bigger than a certain threshold voltage, are those where the transistor is on, and the gate biases that are smaller than a certain threshold voltage are those where the transistor will be off. Can we estimate how much is generally the threshold voltage of a transistor? Well, the answer is obviously yes, and the formula is here. Well, the final formula is this one here actually, but here I'm explaining to you how we can estimate this threshold voltage. So we know that now that the transistor is effectively an MOS device. So it's the gate stack, which is an MOS stack, that controls the operation of the transistor. And we also know that for the transistor to be on, we need to be able to create an inversion layer at the interface with the oxide. So this means that using what we know already from what we did on MOS capacitors, we can say that the inversion layer in the capacitor will be generally generated if the potential applied on the gate of the device is VFB plus 2VF. VFB is the flat band voltage that we've seen some time ago. 2VF, if you remember when we looked at the MOS device and we were dealing with the depletion region, we did see that there was a parameter phi or phi that was effectively used to separate the depletion region from the inversion region. And if you go back and look at those details, we can say that we are for sure into inversion if the surface potential on the at the interface between the semiconductor and the oxide in the MOS device is 2VF or 2VB, whatever was here. We shall use 2VF. Now, on top of this, what we have to consider also is the fact that, and this is why we have this term here, we need to consider the fact that in our transistor, there is a very large depletion charge. So when the transistor is we are turning on the transistor, and so we are creating this inversion layer at the interface with the gate stack. We can have a look probably at this slide. As we said previously, we also have a lot of immobile charges. And as I explained previously, if we were to count those immobile charges, they would be many more than the negative charges that are actually forming the channel. So this is the reason why here, in taking into account the effect of this negative charge that is accumulated at one plate of COX effectively, we are effectively simply counting this depletion charge, because the charge that is forming the channel is effectively negligible compared to that. And so once we realize that the threshold voltage can be calculated with this way, we substitute the values that we've seen some time ago for VFB, phi B, and so on and so forth. And we end up with this very complex formula here. But for the sake of our discussion, what is important is that we know that it is possible somehow with this formula to calculate the threshold voltage. That will be a certain value, and that if the Vg is higher than this threshold voltage, our n-channel transistor will be effectively on, and if not, will be considered off. So now our transistor device is made of 3 terminals: gate, source, and drain. And so we should expect 2 fundamental characteristics, IV characteristics. So the first one that you've already seen is the output characteristic, where we plot IDS as a function of VDS and the free parameter is VG. But then we should also have a transfer or just trans characteristic. Well, we plot IDS as a function of VG. And the free parameter would be VDS, but we can keep just VDS small. For example, 100 millivolt. So let us start with the output characteristic. And we can demonstrate that the output characteristic of a transistor is given by this relation here. As you can see, these are the terms that we've already identified as terms that should be in the position they are, numerator and denominator, Cox W at the numerator and L the channel length at the denominator. And then here the term depending on the voltages VDS and VG, and the threshold as well. So this formula here gives us the output characteristic. What we can see from this formula here is that this is effectively the relation that represents well the output characteristic of the transistor in the linear regime. Sorry. As we can see, the term depending on the voltages represents effectively a parabola as the one that is represented here, pointing with the concavity pointing downward, if you like, because of the negative term here effectively. So this formula is represents the output characteristic of the transistor up to this point here. From this point onward, we know that we are in saturation, and so the output characteristic has to be flat. So while this formula represents well the linear regime, when we are in saturation, what we should consider is that the maximum of this parabola takes place at this point that we shall call VDS saturation. And so by substituting it into our linear regime formula, we can calculate the formula that effectively gives the second part of the output characteristic, that is this one here. So this part of the characteristic is given by this formula, while this part, the first part, is given by that formula. Oh, please note that this term n is a correction factor and is related to body effects and so on and so forth, but for us is a constant anyway. Okay, so we've seen the output characteristic and that it is divided in two pieces, one for the linear regime and one for the saturation regime. Let us have a look now at the transfer characteristic, or just trans characteristic. So the trans characteristic of our transistor has this shape that we see here, and is very simply, because we are assuming here that VDS is small, effectively is arising from the formula we've seen in the linear regime. By assuming that VDS is small, we are effectively able to neglect the term with VDS square. So that's all is happening. So if we look now at this formula here as a function between ID and VG, with VDS a parameter, then we can quickly realize that this is on an ID VGS plot, this is effectively a linear relationship. And so we can quickly realize that the trans characteristic represented by the formula that we have there should be a straight line, like this one. Okay. In reality, what we have in actual terms is the curve that is represented by the dashed line. Okay, but nevertheless, in both situations, what we can see from the trans characteristic is where the transistor is on and where the transistor is off. That's what the trans characteristic does. So as we can see here for our n-channel MOSFET, when VG is smaller than V threshold, and so we are in this region here, the transistor is effectively off, and we are in the so-called sub-threshold region. When instead the VGS is bigger than the threshold, we are in this regime, and so the transistor is on. And so we can be either in a linear regime or a saturation regime, depending on then the specific value of VDS. Now, what is particularly important to note immediately is that in the sub-threshold regime, the current here would seem to be zero, but in reality it isn't. We will see in a moment that actually also the sub-threshold regime could be divided in two sub-regions, let's say. But what is important here, first of all, to note is that the current in this sub-threshold region is actually very complex, as you can see, but most importantly, what I want you to see is that it depends exponentially on the surface potential. And we should remember that the surface potential is piloted effectively in our MOS stack by VG, as we've said now many times. So what happens to the surface potential in the channel is effectively driven by VG. So this means that this exponential dependence of the sub-threshold current from Vs can be effectively seen as an exponential dependence on Vg. And this is effectively what we see, that in the sub-threshold region, the current through the drain and source region is actually exponentially dependent on Vg. And this is what we see here. So here we plot the trans characteristic using a log linear scale. So the Vg is plotted on a linear axis, but ID is on a log scale, so that we can see better the sub-threshold region. That is the one represented in this side of the plot. So we can see that as it is depicted here in this yellow circle, this is in this sub-threshold region here, the current through the drain and source is exponentially dependent on Vg. You can clearly see that this is the current grows exponentially. Once we go beyond the threshold, then we are effectively in a region where IDS is effectively more or less linearly dependent from Vg. And this was this bit of the curve that we've seen previously here. So in this plot, we are effectively now seeing more in detail what is really happening in our transistor. So if we remember that the transistor operates, if we remember that the operation of the transistor relates immediately to the what is happening to our MOS stack, whether it is in accumulation, depletion, or inversion, effectively, we can now try to map directly what our MOS stack is doing with what our transistor now is doing. So we can start from the part that we now have understood, where when the MOS stack is in inversion, the transistor is on. And so we are up here in our trans characteristic. So the MOS stack is in strong inversion. Vg is large, is high, is higher than the threshold. If we now decrease Vg, we will slowly move from strong inversion into weak inversion into depletion. And so that's where we enter the subthreshold regime that is represented here in the yellow and basically represents the moment when the transistor is not anymore on, but is not completely off. And so there is this exponential dependence of the current in this region from the gate voltage. If we keep decreasing now Vg, we turn the transistor eventually completely off because we have moved into accumulation now for what concerns the gate stack, the MOS stack. So when we are in accumulation, it means that at the interface with the oxide, we now have holes. We have positive carriers. And so the channel, the N channel is destroyed. And so we should not have any current passing through due to leakage issues, impurities, defects. There is always a little bit of a current, and that's what we see here. So the trans characteristic of a transistor, if we plot it in a log linear plot as this one, should show these three characteristic regimes that map perfectly with what we know is happening in the MOS gate stack. Now, if we look a bit more in detail to what is happening in the subthreshold regime, what we realize is that we would like to try to quantify a bit more this subthreshold behavior that we just mentioned, where we have this exponential increase of the channel current as Vg approaches the threshold. So when we move Vg in this direction toward the threshold, the channel current increases exponentially. So can we quantify this behavior a bit better? The answer is obviously yes, and it is quantified through a parameter that is called the subthreshold swing. This parameter is extremely important because it's telling us how we move the transistor from being completely off to being completely on. So how fast we move from this region to this region is quantified by the subthreshold swing. And the way to quantify it is through this formula here. So is by calculating on this log linear plot the slope of this that I've indicated here effectively. And in practical terms, this is dVg over d log id in the subthreshold region. And we can demonstrate that this quantity here can be calculated analytically, and it comes down to this. So S is kT over Q, so the thermal energy kT, ln10 time a term that depends on capacitances that are related to our transistor geometry. So we have CD is the depletion capacitance, Cox is the gate capacitance, and CIT is the capacitance associated to interface traps in case we have any interface traps at the silicon oxide interface. From this formula, what we see is that in case that this term is negligible as compared to 1, the swing has a lower limit of 60 millivolt per decade. As you can see in the plot I've shown here, these data I've shown you here are data from a real transistor. So this transistor has a swing of 127 millivolt per decade. So this is clearly telling us that we are still quite far in this case from the lower limit of 60 millivolt per decade. Please note that for what concerns the swing as a parameter, the smaller it is, the better it is. Let me just clarify something I said previously, that the swing quantifies how fast the MOSFET goes from the off to on condition and vice versa. Now, this term fast is meant there in the sense that how many volts do I need to change VG in order for the transistor to go from off to on or from on to off. This is the meaning. So it's not meant in terms of time there, fast, but is how effectively how far in terms of volts, if you like, are the on and off condition of the MOSFET, and correspondingly how many orders of magnitude will correspondingly change the current through the channel. So, for example, as shown in this plot, the swing is 127 millivolts per decade. This means that if I am in the off condition, every time I change VG by 127 millivolt, the drain current should increase by 1 decade. That's what this means. So obviously, if I was in a better situation, as we said previously, the lower limit for the swing is 60 millivolt per decade. So every time I increase VG by 60 millivolt, the drain current in the subthreshold regime would increase by 1 decade. So be very careful that fast here is used in these terms. Let us have a look now at more in detail into the charge distributions in our MOSFET as it operates. We've said previously that the key operating principle of the MOSFET transistor is that when we apply gate voltage VG that is bigger than a certain threshold, then we create a channel in the transistor made of minority carriers, that in this case will be electrons, that bridge the source and the drain. At the same time, it is very useful to understand what the other charges are doing and what are their distributions. Before I continue on this point, we need to, in order to do this properly, we should realize that when we think of a MOSFET transistor, we should remember that in the semiconductor that represents the substrate that also contains the source and the drain regions, effectively we have two p-n junctions. The p-n junctions between the body and the drain, and the p-n junction between the source and the body. So we can call the first one DD, the drain diode, and then the other one DS, the source diode. And we should remember from what we said on p-n junctions that when we are dealing with a p-n junction, depending on how it is polarized, the depletion region at the p-n junction interface can be very large in case of a reverse bias p-n junction, or can be very small in case of a forward bias p-n junction. So keeping that in mind, we can now try to relate this to the operation of the transistor. More in particular, if we assume that, for example, as we said previously, that the source in our transistor is our reference potential is always at 0 volts. When we apply a VDS voltage that is positive, effectively what we are doing is we are reverse biasing the drain diode, and we are forward biasing the source diode. So this means that we should expect between the drain and body interface that is along this entire interface here, we should expect a large depletion that will extend into the body, into the P side, while for the source and body interface, that is this one here, we should expect a small depletion because this p-n junction is slightly forward biased, as we will discuss in a moment. So if we go back to our transistor, when we apply a certain gate voltage and VD is small, very small, then we could say that we have our inversion layer here, and this dashed line is indicating us the extent of the depletion region. So here we have our P carriers, and between the solid line and the dashed line here we have a depletion region. So when VD is very small, both on the source side and on the drain side, we could say that more or less the same thing is happening. But if we now increase VD as we do here, and we can imagine, for example, that VD is VD sat. So in this situation, what is happening now is that as we said previously, the drain diode, the p-n junction at the drain interface, is reverse biased, so there will be a large depletion as indicated here. On the source side, on the other hand, the source will be slightly forward biased, and so the depletion will be the depletion region will be extremely small there. So as we can see, the depletion region that spans now effectively across the entire device is not uniform. And if we keep increasing VD, we see that the depletion region due to the reverse biased p-n junction at the drain extends now well beyond the proximity of the drain junction, and starts to effectively to expand into what we would call the channel area. And this is what causes also the pinched characteristic of our transistor, and the saturation and so on. At this point is worth noting what is happening with this inversion layer as we increase VD. Now, what I would like to point out here is the exact shape of the inversion layer. If you look closely, the inversion layer, as we increase VD, is moving, is being pushed toward the source region, as we can see here. So the inversion layer is being pushed toward the source region of the channel. This is in contradiction, if you like, to what we had said at the very beginning when we were qualitatively looking at the operation of the MOSFET transistor that was on this slide here. So as you can see here, while we were qualitatively discussing the transistor, we have drawn the inversion layer under the influence of a certain positive VD in a way that is showing basically that the inversion layer is being pushed towards the drain. So in reality, we had said already at that time that we would look into the more details into what is really happening, and so what we've said at this point in order to qualitatively understand what is happening is fine. So it's not a problem. But when we look into more details to what is really happening, what we need to realize is that the inversion layer actually is pushed toward the source because there is a huge depletion region on the drain side. So you remember that the depletion region is made of immobile and negative charges. So it is this huge asymmetry in immobile charges between the drain side and the source side that explains why the inversion layer seems to be moving in the wrong direction. Okay, remember that here the electric field is directed in this way. Okay, so it would seem that the electrons are moving in the same. The electrons in the inversion layer are moving in the same direction of the electric field, which shouldn't be obviously according to Coulomb law. But the reason this is happening is that because they are being repelled by the huge amount of immobile negative charges that are being, if like, exposed into the depletion region under the drain. And so when we increase VD beyond the saturation voltage VD sat, then the depletion region under the drain is so big that effectively the inversion region in the channel region is effectively crushed, pushed toward the source side. Okay, so what we said several slides ago at the very beginning, qualitatively, let's say, it was good to understand what is happening qualitatively, but remember that the picture is a bit more complicated, as we've just discussed here. So we need to take into account actually these depletion regions to actually understand what really happens. Okay, since we've got a look now at the charge distributions in our MOSFET devices, it turns on and starts operating. Let us have also a look in a bit more detail into the energy diagrams of our device as it starts operating. So let us imagine that we have our MOSFET device. Here is shown in a cross-section. So we are looking at our device from the gate effectively, and we look into the depth of the silicon now. So we have our source, our drain, and our channel effectively here, and the gate stack on top. And so we are now trying to imagine to see a three-dimensional version of an energy diagram of this device as we move along the let's say x-axis here, from the source into the channel and then into the drain. So let us imagine to draw the energy diagram when the device is in a flat band condition. So when we are in a flat band condition, bands are, as the term says, flat, and so it should be a relatively easy thing to draw. Remember that we need to maintain the fundamental rule that the Fermi energy is the same across the entire semiconductor. So as you can see, this is the dashed line here, and then we have the source is represented by this n-type energy diagram here. Then we have the P region and then the N region. So this effectively represents the energy diagram in the depth of the device. So we are looking into the depth of the silicon substrate, starting from the very interface with the MOS stack on top into the depth in this direction. Okay. So we are assuming that what we see in front of us, what is facing us, is actually what we would see at the interface. So when VG is bigger than V threshold, but VDS is 0, so we are turning on the transistor, but there is no current flowing through the channel, we would expect that the band diagram, the above band diagram becomes like this. So as you can see, near the interface with the oxide, with the MOS stack, we are pushing down the energy diagram of the P side. We are making, as you can see, the energy, the Fermi energy that is here is closer now to the conduction band. This means, as we said previously, we are inverting the semiconductor locally and we are turning it into n-type. And so now, as you can see, electrons from the source or the drain using thermal energy could potentially overcome this barrier. Obviously now there is no VDS applied across the source and the drain, so there is no reason why electrons would prefer to move from one side to the other or the other way around. So the current in this case is 0. If we then apply though a VDS bigger than 0, so we, as we know now, applying a positive voltage on the drain means that we push down the drain side of the energy diagram, and so we end up with something similar to this. So as we see now, an electron here can effectively and happily move into the drain side. But this would happen only very close to the interface with the oxide, as you can see, because an electron that is in the depth of the silicon substrate would not be able to do that, because probably has to overcome a barrier that is too high. Let me stress here a very important point that we will touch again very soon when we deal with the scaling issues of a MOSFET transistor. If we look at the energy diagram of our semiconductor, of our drain, channel, source regions, but very, very close to the interface with the MOS stack, we should be able to see what I've drawn here. So when we are at flat band, we have the black curve, as we explained previously. Then as we apply a gate voltage above the threshold, we are inverting the channel, and so we get the red curve here. And then when we apply also a certain drain voltage, we get the green curve. Now, I want to stress the shape of this curve here, because as you can see, acting the application of VG or VD affects only the channel region or the drain region respectively. So VG clearly controls the channel, while VD clearly controls just the drain region, and just a little bit very close to the interface between the drain and the channel region. So the two parameters that control the operation of my MOSFET also control two different regions, physical regions in my device. And this is fundamental. When it will, we will see, we will come to analyze the scaling challenges of this device. So, summarizing what we've said up until now regarding the general operation of our MOSFET transistor, we can say that when the transistor is on, which means that VG is bigger than V threshold, we can be in either a linear regime that is characterized by the fact that VDS is smaller than a certain VDSAT. We've seen which is the relation that gives the value of VDSAT, or we can be in a saturation regime that is when VDS is bigger or equal than VDSAT. And on the other hand, the transistor is considered off if VG is smaller than V threshold. Okay, let us have a look now to the scaling challenges of MOSFET transistors. So we have already briefly highlighted the major challenges that are there when we try to scale electronic devices. These are, if you remember, the things that we've said when we were talking about Moore's law and the general problems that scaling poses to the shrinking of electronic devices. So here we would like to have a look more in detail to the specific issues that are related to MOSFET devices. The fundamental problem goes under the name of short channel effects. And the MOSFET transistors that suffer from short channel effects are all those transistors that have a channel length that is below 1 or 2 microns. And the major problems that arise when we deal with the short channel transistor are those 5 that I've written down here. So we will discuss the drain induced, barrier lowering, and the drain punch through, subthreshold swing degradation, and increased subthreshold current. This is also related to point 1. Threshold voltage variations. This is also related to point 1. Velocity saturation, mobility degradation, and gate oxide leakage current. So let us start by considering what is the drain-induced barrier lowering. What do we mean by that? So we've just seen a few slides ago that the key point in the operation of a standard long channel now, if you like, MOSFET transistor is that the operation of the gate transistor relies on the fact that the gate affects clearly just the channel. The drain affects, the gate voltage affects just the channel, and the drain voltage affects just the drain, or in the interface with the channel region. And this is what this diagram here is reminding us once again. So when there is no VDS applied across the MOSFET transistor, and initially when VG is equal 0, the energy diagram is this one here. As we apply a VG, a positive VG, what happens is that the conduction band in the channel is pushed downward, and so we turn the transistor on. At this point still there is no current because the VDS is 0. When we then though apply also some VDS, what is happening is that we are pushing down here VDS, we assume VDS positive here, we push downward the drain side of the energy diagram, and so now some electrons could potentially flow in this direction. And so we can see that the channel is completely and mainly under the influence of the gate bias. So the gate voltage is in full control of the channel, and that's the key point. Now the drain-induced barrier lowering is related to the fact that as we shrink our planar MOSFET transistor and into the region where we said we have short channel effects, then effectively what happens is that the gate does not have any more full control of the channel. This is what these diagrams here are showing us. So again, let us imagine that we are in a short channel transistor, MOSFET transistor. So VDS is 0 here, or anyway extremely small, and we are plotting here again the energy diagram when VG is 0 and when VG is some positive value. So when there is no VDS applied across the device, it would seem that everything is working fine, and the gate voltage is indeed in control of the channel. But if now we consider the energy diagrams when in presence of a certain VDS that is positive in this case, so we can see that the drain side has been pushed downward, well, the energy diagram seems extremely deformed, if you like, as compared to the previous case. So again, this is the energy diagram when VG is 0, and this is when VG is positive. So what we see here is this extremely deformed energy diagram, and if we compare the energy diagram, the dashed line here with the dashed line that we've seen before here when VDS was 0, what we clearly realize is that this skewed energy diagram here is now arising from the fact that VDS is non-zero. So this means that now VDS is having an effect into the channel. So in a short channel device, the drain-induced barrier lowering arises from the fact that the VDS has now an effect into the channel. And so if we compare now the situation where VG is positive, and we get this energy diagram here, and we compare it to the case where there was no VDS, we can clearly see that the effect arising from the presence of a VDS in this case is effectively that the barrier seen by the electrons that wanted to move through the channel is now much smaller than the barrier that we would have had if the transistor was a long channel transistor. So you can see that this deformed diagram is effectively telling us that the electrons now in a short channel transistor have a much smaller barrier to overcome, and this deformation is under the control of VDS and not of the gate. So the drain-induced barrier lowering is exactly this, so that the application of a drain voltage is inducing a barrier lowering into the channel. So we are in a very unfortunate situation here where the channel is not anymore in full control of the gate voltage, but now this control is shared between the gate voltage and the drain voltage. And the reason why this is happening is because of the very large depletion region around the drain, and also the much smaller one, although in the source region, that they both extend now well into the channel area. So effectively, if L was the intended channel region, the true channel region now is actually L prime. And the short channel effects arise because in this case L prime is becoming much smaller than L. So it is only the region that we denoted with L prime that is actually under the full control of the gate. All the other regions are under the control of VDS. Oh, please remember that we used to have, as we pointed out some time ago, we used to have these depletion regions also in long channel transistors. But the point is that in a long channel transistors, these depletion regions are the extension of these depletion regions within the channel regions is negligible compared to the actual size of the channel. So in other words, what I'm saying is that in a long channel, L prime is roughly equal to L, because the channel is so long that we can effectively discard the extension of these depletion regions into the channel. But in a short channel device, this is not anymore the case. And the actual part of the channel that is under the control of the gate is actually now much smaller than the intended channel region. And this the process of shrinking a long channel transistor into a short channel transistor is highlighted by this sequence of diagrams. So we shrink when we move in the downward direction here, and so we can visualize what is happening to the energy diagram of my channel as we move this way, and so we can visualize the DIBL effect, the drain-induced barrier lowering that we just mentioned. That is in this case highlighted by this lowering here, as you can see. The drain-induced barrier lowering, which, as we said just a moment ago, arises because now the channel is controlled by the gate voltage, but also by the drain voltage, has other knock-on effects on other parameters. The first one is an increased subthreshold current, leakage effectively. And the reason is here is extremely simple. It is simply down to the fact that now the source and drain regions are becoming closer together. And so there is higher chances then that charges can travel through the bulk of the material from the source to the drain, and so and vice versa. So when we shrink the device, we should expect that the subthreshold current increases, especially the current that down here, for example, that is represented in this diagram, that indicates the current that we would get when the transistor is completely off. Okay, when the MOS stack is in accumulation. So as you can see, this current, as we shrink the transistor, the channel moves upward. Another effect is the deteriorated, increasing subthreshold swing, as again shown in this plot by these fitting lines in red that I've shown here. So as you can see, the swing is deteriorating. So the slope is decreasing on this diagram, which means that the swing, which is 1 over the slope of these curves, is actually going up. And so this means that the gate is no longer able to switch quickly the MOSFET from the off condition to the on condition, and vice versa. And this obviously is related to the fact that the gate is losing control as we shrink. The transistor is losing control of the channel. Another important effect is the decrease in threshold voltage. This is highlighted here by these two graphs in two ways. So the first graph is showing us that if we were to plot the threshold voltage of our MOSFET transistor against the channel length, we would see that the threshold voltage is constant as long as we are in a long channel transistor. But if we then enter the short channel situation, the threshold voltage will start to drop. And in this case, the reason is can be understood by obviously reminding that the channel is not anymore fully under the control of the gate voltage, which means that only a small portion now of the channel is under the direct control of the gate voltage, which means that less charge is required to create the inversion layer required to create the channel, and so this means that less voltage is required to create the inversion layer. And so this means a smaller threshold voltage for the transistor. But also there is another effect, and the effect is the second effect is represented by the second plot of the threshold voltage against the VDS, the voltage on the drain and source contacts. So in a short channel device, what we see is that, because we've said that the channel region now is partly controlled by the gate and partly controlled by the VDS, this means that we should expect VDS to have some effects on the threshold. And this is what this plot is showing us. As we can see, when VDS is small, the threshold voltage of the transistor has a certain value, but if we operate the transistor at a higher VDS, we should expect that the threshold voltage drops. And this is because, as we've seen in the energy diagrams, the threshold voltage, the channel of the transistor is under the influence of the drain voltage, and the drain voltage modifies the barrier seen by electrons traveling into the channel area. And that is why the threshold drops as we increase VDS. Well, the way we can minimize a little bit the effects of drain-induced barrier lowering are those listed here. We could, for example, increase the doping level in order to make the depletion regions smaller. This is something that we've realized some time ago in chapter 4 when we discussed the PN junction. Or we can, for example, replace the thick source and drain doped regions with shallow doped regions, so shallow junctions. This also would avoid the creation of very large depletion regions. The problem, though, with this solution is that by reducing the volume of the drain and source contact, effectively we are increasing the resistance of that piece of material. And so this is really something that we don't want. In any case, what is definitely true in the case of a planar MOSFET transistor with short channel effects is that the threshold voltage control is always problematic. And so that is why we need to explore different device configurations in order to fully solve this problem. That's what we will have a look at later on in this chapter. So let us explore other problems arising from short channel effects in our planar MOSFET device. So the other problem we mentioned is velocity saturation and mobility degradation. This phenomenon arises from the fact that up until now we've said that the charge carriers in a semiconductor, in a piece of material under the influence of an electric field move at a speed that is proportional to the electric field, and that the proportionality factor between these two quantities is called mobility, according to this formula here. Now, the problem is that this is true if the electric fields are small. In reality, we know that a more correct investigation of this into this relation highlights the fact that in reality the relation between velocity of the carriers and electric field in the semiconductor, for example silicon, should have the shape that I've shown you here. So there is in the low field regime the velocity is proportional to the electric field, and we will call this region constant mobility region. And this is the one we've been referring to effectively up until now in our long channel devices. But if the electric field is above a certain critical value, that in the case, for example, of silicon is of 1.5 volt per micrometer, then the velocity saturates, and so we enter the so-called constant velocity regime. Now, why we are interested now in this, the reason is very simple. And as we've mentioned in chapter 1, while we scale devices and technologies, there has been a problem in scaling at the same time the voltages used to operate these devices. Actually, as we've seen in chapter 1, for quite some time now, voltage has not been scaling almost at all. So we have the voltage, the operating voltage of devices that is not scaling, while we are scaling the feature size of the devices, which means that, in other words, the electric fields in the newly generated devices is actually going up. Remember that the electric field is the voltage applied divided by the distance across which we are applying this voltage. So in our scaled devices, effectively the electric fields are going up. And so if the electric field goes up, at a certain point it will go above the critical electric field that we just mentioned, and so the velocity will saturate. The velocity of the charge carriers that are drifting because of the applied electric field will actually saturate. And so in reality, when we are dealing with short channel effects, or there is a danger that there might be short channel effects, we need to use a different formula to relate the speed of the charge carriers with electric field. And this formula is the one that I've shown you here. This is a reasonable approximation of the curve that I've drawn here in this plot that has this saturated behavior here. So in this formula here, μn is the constant mobility that we would get if the device was a long channel device. And as you can see now, the electric field appears also in the denominator. So if the electric field in this formula is small, much smaller than EC, we go back to the formula we know, the constant mobility formula. But if the electric field is not small, then the effective mobility that is represented by the terms in the circle here is effectively dependent now from the electric field. So the actual electric field, the actual mobility of my device is μn over 1 plus E over EC. And so it becomes electric field dependent, or voltage dependent if you like. And so we need to take into account this dependence if we want to understand how the transistor now affected by short channel effects will behave. So in order to understand that, let us explicitly write down our mobility here as according to the term we just mentioned, so μn over 1 plus E over EC, and we will write explicitly now the electric field as VDS over L. So remember, L is the length of the channel and VDS is the voltage difference applied across the channel. And so, as we've just mentioned, if the electric field is small enough, which means effectively that we are in a long channel transistor, the mobility is effectively the mobility that we've dealt with up until now, the constant μn. But if we are not in a long channel transistor, we are in a short channel transistor, then we need to take into consideration the exact value of the electric field. So if the electric field is lower, the electric field in the channel is smaller than the critical value, we can still consider this value of the mobility. But if not, we need to say that the mobility is actually given by this formula. And so if we neglect now, if we assume the E is much bigger than EC, then we can neglect 1 here, and we can then write that then effectively the mobility will be this one. So this is the value of the mobility that we will assume when we are in a constant velocity situation that we know is when we have when we are in presence of short channel effects. And this μn, remember, is still the mobility that we would have got if the device was a long channel. So it's actually the mobility of the piece of semiconductor we are using for the channel. So using this this approach now, we will try to rewrite more clearly how the output and transfer characteristic of our transistor changes when we go from from long channel to short channel. And this is what we do here. So let us first consider a long channel transistor and remind ourselves how we write down fully the characteristics of our device. So If the transistor is on, so which means that Vg is bigger than V threshold, the output characteristic is given by this formula here for ID. When remember, this is for in the linear regime, so when VDS is smaller than VDSAT, or is given by these formulas here when we are in the saturation regime, so when VDS is bigger than VDSAT. Please note in these formulas here that IDSAT, so the saturation current, depends quadratically from Vg minus V threshold. Okay. Let me just point out, because I didn't say this previously. So in the output characteristics of our transistor, we've often seen a parabola being drawn that was separating the linear regime from the saturation regime. So this parabola is actually represented by this ID SAT. You see, if we, please note that in these formulas I'm neglecting n. I'm assuming n is 1, the non-ideality factor that we mentioned previously. If we look at ID SAT and we substitute VD SAT there where we see Vg minus Vt, we can actually see that D SAT is proportional to Vd SAT squared. And that's exactly this parabola that we have seen many times drawn on top of output characteristics of long channel transistors up until now. Okay, but what this is also saying to us is that when we go from one to the next, we do that in a quadratic way, so Vg minus V threshold squared. So every time, remember that when we go from this curve to the next one, we are changing Vg. So this change is following a second power relationship according to the IDSAT formula there. And regarding the transfer characteristic, we've seen that for Vg, again, when the transistor is on, the transfer characteristic is given by this formula here. Okay, so this is for a long channel transistor that we've been dealing basically up until a few slides ago. Let us now see how we can transform these very nice and clear formulas when we are dealing with short channel transistor. And this is what we are doing here. So in presence of short channel effects, so we need to take into account that the mobility can take two values effectively, the ones that we've highlighted here. So for at low electric fields, the mobility can be effectively just this term, or at high electric fields, when we are above the critical electric field of the semiconductor, it will become this value. And so we have to separate these two situations. That's what is happening here. So again, when the transistor is on, that means Vg is bigger than V threshold, we have that the output characteristic is given now by this formula here when the electric field in the channel is smaller than the critical electric field. And so basically the short channel transistor is effectively operating like if it was in a way a long channel one. So the mobility is still the mobility of the corresponding long channel transistor. So as you can see, this formula is exactly the same as the one that we've seen in the previous slide. But if we increase now the electric field in the channel above the critical value, then we could substitute in the formula there where we see me, this new value of the mobility that is field dependent. As you can see, the mobility now depends on VDS. So as we increase VDS, the mobility effectively is dropping because of the mobility degradation we mentioned before. And so effectively the output characteristics should change to this one now. Oh, note now that in this case, the Vg minus V threshold term in ID sat is now linear. So this is one point to note as compared to the long channel case. And now Vd sat is given simply by the critical electric field. It's related maybe to the critical electric field. Oh, note that this Vd sat here, if we were to calculate it, this is generally much smaller than Vg minus V threshold for our specific transistor. So this means that short channel devices saturate earlier than long ones. That's basically what this is telling us. And regarding the transfer characteristic, again, we need to separate the low field to the high field case. So when we are in the low field case, the ID is given by this formula here, which is exactly the same as the one that we've seen for the long channel case. But then if we go above the critical electric field, we enter the velocity saturation regime, then the ID changes to this one. Oh, it is very interesting here to note that when we are in velocity saturation regime, the currents, the ID, the current in the channel is independent from L. So this is quite a remarkable result. It doesn't depend anymore from the length of the channel. And so if we were to visualize these effects, we would end up with something like this thing that I've drawn in this graph here. So imagine to have exactly the same MOSFET transistor, and we simply change L, and the change is such that we effectively are going from a device that is long channel, say, I don't know, that the L was 5 microns, and we go to a new L that is effectively short channel. So for example, I don't know, 500 nanometers. So the change in the ID VDS output characteristic would be the one shown here. So the long channel device would have this output characteristic for any given Vg value, while the short channel one would be this one. So as you can see that effectively the device is saturating much earlier now. And also there is a remarkable decrease in the current that the device is passing through the channel. This is obviously due to the velocity saturation phenomenon and mobility degradation. And we can even better visualize these things by comparing a real device now here. So we see here this is the output characteristic of exactly the same transistor, but these two transistors differ only by the value of L. So in one case L is 10 micrometers and in the other case is 0.25. So this is a fantastic example to observe the effect of the velocity saturation on the output characteristic. So the long channel transistor has these characteristics shown here in this plot. And so we can see the parabola that is separating the linear regime from the saturation regime. But when we move to the short channel device, we see that first of all the threshold, VD sat is much smaller now than in the long channel device, and also that the spacing between the different curves is now following a linear relation and not anymore quadratic as it was here. So the current, if you notice, the currents are also smaller. Okay. Another of the very big problems that arise in scaling the transistor is the increased gate oxide leakage current. Indeed, as we've seen in chapter 1, when we said that we need to scale down the transistor, this means that we need to scale it down in all directions, and so we need to scale down the size of the length of the channel, the width of the channel, but also the gate stack on top of it, which means also scaling the thickness of the insulating layer between the gate and the channel. And by doing so, if we scale too much the insulator that traditionally is made of silicon dioxide, then at a certain point we will see that direct tunneling taking place there it cannot be neglected anymore as we approach, few nanometers thickness. So this is obviously a big problem. We've seen this in chapter 1 very briefly and rather qualitatively, how this can affect the leakage current overall of the transistor, and so the standby current, and so on and so forth. So people have tried to address this problem in a clever way, that is to replace silicon dioxide with a material with a higher dielectric constant, trying to keep, though, the capacitance the same. We will come back to this point later on also when we deal with non-volatile memories, but the requirement of keeping the capacitance of the gate stack the same, unchanged, relies on the fact that when we operate, the gate stack is a capacitor, and so this capacitor together with the transistor is generally connected in a matrix of transistors, and so normally there will be some resistance connected to these connections that are made. So very simplistically, there will be a resistor and then our gate capacitor connected. So this RC circuit, as you probably know, immediately points us to the fact that in operating my gate stack, so in operating basically the capacitor that is on the gate, there is a charging and discharging process. It's not instantaneous, the operation of this capacitor. So there is always a time constant tau that is given by this, where R, remember, is resistance, for example, that could be related to the interconnecting wires that connect the gate of the transistor to the outside circuitry of the whatever device the transistor is used for. And so this time constant tells us, how fast the gate stack can be operated in a way. So how quickly I can change the voltage on the gate, how quickly I can increase it, how quickly I can reduce it. It's all related to the charging and discharging of the capacitor C through the resistor R. And so if we were to change, in the scaling process, if we were to change C, this would change the time constant, and so the speed at which my transistor effectively could eventually operate. And we don't want that, of course. So that's why technologically there is this constraint, let's say, that when within the same technology node we try to modify some of the components, let's say, involved, in this case the insulating layer of the gate stack, we try to keep the relevant parameters unchanged. So in this case, we would keep the capacitance constant, the capacitance of the gate stack. So and this is exactly what I'm doing here. So let us assume that we want to, during the scaling process, our insulating layer that used to be made of silicon dioxide is now becoming too thin, and direct tunneling is a problem. So what I want to do is to change to a high-K material. Let's say there is no reason to, at this point, to say what material is that, but what we need to do is to impose an equality between the capacitance of the new insulating layer and the capacitance of the old silicon dioxide insulating layer that I used to use. By imposing this equality, we immediately realize that this equation is the equation that tells us which must be the thickness of this high-K insulator that I need to use in order to replace my original silicon dioxide. And you can see that the proportionality factor is effectively the ratio between the dielectric constants of the two materials. And as we can see immediately from this formula is that because this ratio K high K over K SiO2 is by definition bigger than 1. Remember that with by high K, we said we characterize all those materials that have a dielectric constant larger than the one of the silicon dioxide. So it's clear that this factor is bigger than 1. We would try always to make this factor as big as possible. So it could be, I don't know, 5, 10, whatever. So this immediately tells us that by following this route of changing the insulating material for a high K one, we end up with effectively a film thickness D that is much larger now than the original one. And this can be a very good cure to the problem of the increased leakage current through the insulating layer that was originally made of silicon dioxide. So using a high K material instead of silicon dioxide has helped a lot in solving the problem of the gate oxide leakage current. For example, just to put some numbers down, so let us imagine that we want to replace silicon dioxide gate material with hafnium dioxide. So silicon dioxide has this dielectric constant 3.9, and let us imagine that the original thickness was 2 nanometer. So when we replace with hafnium dioxide, we recall that hafnium oxide has a dielectric constant nominally of 25. So the thickness of the equivalent from the point of view of the total capacitance hafnium dioxide film is 12.8 nanometers. So this is a remarkable, obviously, improvement from the point of view of tunneling current. Indeed, if you do the calculations, and recalling that the tunneling current depends exponentially from the barrier thickness, from barrier width, we can immediately realize that this above the above change should potentially reduce the leakage current by more than 4 orders of magnitude, which is obviously quite remarkable. Since we are talking about changing the electric materials and using high-K materials, it's quite important to clarify a term that is widely used, especially when we deal with high-K materials, and this is the concept of equivalent oxide thickness. So the equivalent of given a high-K dielectric film, we will call equivalent oxide thickness of that high-K material the thickness of the silicon dioxide layer that has the same capacitance. So effectively relates to what we just said, simply looking at it from a different point of view. So the equivalent of oxide thickness of high-K material is given by this formula here. So is the thickness of the hypothetical silicon dioxide layer that would have the same capacitance of my high-K film. So if you notice, this is simply the formula we've seen previously in the previous slide in a reversed way, if you like. And if in the case of our 12.8 nanometer hafnium dioxide film, we would say that the equivalent oxide thickness of this 12.8 nanometer film would be 2 nanometer. So the equivalent oxide thickness has this meaning. So this is a way that people have found to be able to compare the properties of quickly to compare the properties of different high-K films. Okay, so we've had a look up until now to all the challenges, or the main challenges that we may face when scaling down a standard long channel transistor. In this table, there are now some opportunities also that we may be presented with in improving these problems that could arise. There are here obviously several things that someone could do. We've seen already some while we were discussing the potential problems. Here I would like to have a look at a few of them, just because I think are interesting. So I would like to briefly discuss with you strain, the use of strain to improve things, ballistic transport, and the use of high mobility materials, and the use of halo pocket implants. Let us start with strain. So in microelectronics, the strain is used to effectively modify the effective mass of the carriers in a material, in the strain material. The idea is obviously relatively simple. We use let us imagine that our channel of our transistor is made of this material here, which has a quite large lattice. So in order to modify the effective mass of the carriers, what we do is, and so to strain the material effectively, what we do is we put this our original material in generally a very thin film of that material on a bulk a piece of material that has a smaller lattice. So when we put our red lattice here in contact with the bulk material that has a smaller lattice, what happens is that the top layer that used to have a larger lattice is compressed in order to match the lattice beneath. And so it undergoes, in this case, for example, we could imagine a compressive biaxial strain, or biaxial because we could imagine here that the compression is happening on the plane of our film, so in both, for example, X and Y. In other cases, the strain could be uniaxial. Just in one direction, okay? But for example, in this case could be biaxial. It doesn't matter. But what is important here is that this process of creating this compressive strain effectively enhances the mobility because it is modifying the effective mass of the carriers in that strained material. Oh, please remember that the effective mass is related to the curvature of our parabolic band. So if you remember, in the parabolic band approximation, we have that the energy of our electrons in that specific band is given by this formula here. So the curvature of this parabola is given by this term here, is h bar square over 2m. So as we can see, if m becomes smaller, the plot of the EK dispersion relation becomes this one here in red. So a smaller effective mass corresponds to a sharper band diagram. And because we know that the effective mass of the charge carriers in that band is immediately related, if you remember, to the mobility in an inverse relation. This means that reducing the effective mass effectively means that we are increasing the mobility. And this process can actually produce huge increases in mobility. You can see here an N MOSFET where a strain has induced a doubling effectively of the mobility values at several electric fields. So strain has been effectively used for quite some time, and still today is used as an effective tool to further modify and improve the mobility of our charge carriers in the channel. Another way to improve things and ease, if you like, the effects of the scaling process on our MOSFET transistor is to use effectively materials that are intrinsically higher mobility. So you can see on this plot the mobility versus the different materials, silicon, germanium, and so on and so forth. So in red you can see the mobility for electrons for that material, and in blue the mobility for holes. So you can see that really silicon, in terms of mobility, intrinsic mobility of the charge carrier, is not doing really great. So we could definitely benefit from changing silicon to other materials. Remember though that I should stress this, as we've said, I think this some time ago, one of the reasons that the semiconductor industry is based on silicon is not because silicon is a great semiconductor. As this plot is showing us, this is not really the case. Silicon is not really a good semiconductor, as we can see here. The mobility is not great. But the reason we use silicon is because it has a great insulator, a great oxide that comes with it. And that's why the tandem silicon dioxide have effectively driven the microelectronic and nanoelectronics revolution. So if we decide to move to a different semiconductor that has intrinsically a higher mobility, the big question we need to ask ourselves is, what are we going to do for the insulator? So that's one of the big challenges there. That's why there has been, a lot of research in high-K materials and how they interface with different semiconductors and so on and so forth. So it is a field where there is really a lot to research, and there is a lot of technological development that is required. Okay, ballistic transport. So we've mentioned ballistic transport some time ago, and we've already said that in a piece of material, in the bulk of a piece of material, normally carriers drift, and they undergo scattering processes. And it is only when this piece of material becomes small enough that scattering at a certain point may cease to happen. When the distance charges need to travel is smaller than the mean free path of our charge carriers, we may not see anymore any scattering phenomena. And so in this case situation, we will say that we are in a ballistic regime. And we've gone through a little bit some of the formulas involved here. I repeat a little bit some of those concepts. So the mean free path for any given charge carrier could be written down as the thermal velocity time, the coherence time, and where the thermal velocity is related to the thermal kinetic energy of those charge carriers. And the mobility we've said is given by this formula here. And so using these two formulas, we can easily calculate that the mean free path for a charge carrier is given by this formula here. And if we put the numbers in for silicon at room temperature, we can realize that this mean free path is of the order of 10 nanometers. So nanoscale transistor could actually be ballistic. So this is obviously a desired feature. That would definitely improve the properties of my transistor. But obviously there are other problems, as we've seen, when we try to scale things to this level, to such a small nanoscale level. Okay, the last thing I would like to mention here is the point regarding halo and pocket implants. So we've briefly mentioned this when we were talking about the drain-induced barrier lowering. So the halo and pocket implants is a way to reduce the effect of the negative effects arising from the scaling process through the DIBL phenomenon, the drain-induced barrier lowering. And the idea is extremely simple. Effectively, you need to create, as you approach the drain and source highly doped regions have to be graded. So they have to be ideally extremely shallow in the vicinity of the channel area, and then they can become thicker and thicker as we move away from the channel. So this is a very nice technique to reduce the depletion regions in the close proximity of the channel, and it has been effectively used for quite some time to and still today effectively is used to prevent any negative effect due to DIBL into the channel area. Okay, so up until now we've had a good look at how the MOSFET transistor operates, and which are the scaling challenges, the problems that arise when we shrink this MOSFET transistor into the nanoscale, and how in a way we can tackle some of these problems, which are the techniques that people have been using to solve these problems. But I think that we all agree that the most worrying short channel effects that we've seen up until now is definitely the fact that when we shrink the MOSFET transistor, the gate may lose control over the channel. So This is really the most catastrophic effect of the scaling process, because as we've said, the transistor is a field effect device. So if the gate loses control over the channel, there is no transistor anymore. So since we've started realizing that there are short channel effects in a standard planar MOSFET transistor, as I'm thinking now to the many diagrams we've seen up until now, where our transistor is the standard planar device with source and drain and gate stack on top. So people have been trying to come up with ideas that could help in giving back control to the gate over the channel. There are several approaches to this, and there are in particular planar approaches and non-planar, so 3D. And so here we will have a brief look at these ideas and how we can increase the control of the gate over the channel. We need to become familiar with some acronyms that we will see. So the first one is the term SOI, which means silicon over insulator. SG or DG means single gate, double gate. PD or FD, partially depleted, fully depleted. UTB, ultra thin body, and the GAA, gate all around. So the 2D planar of configurations that people have come up with are all based on SOI MOSFET, so on a silicon insulator MOSFET, and can be single gate or double gate. And there are non-planar structures that are more recent, and it is the FinFET and the gate all around MOSFET. We will also have a brief look in few slides on more advanced nanoscale transistor approaches that are basically related to the tunnel transistor and the single electron transistor. Okay, so but let us have a look first to this planar approach. This was the first one that people have come up with to try and solve a little bit the problems arising when scaling the MOSFET, the standard planar MOSFET geometry. And the idea of using the SOI technology, the silicon on insulator technology, relies on the realization basically that in a standard MOSFET transistor, that is the one that is shown here, the gate has control of the channel, which is the region near the interface with the insulator, but the gate has no control over what is happening deep into the bulk of the silicon. Remember that the body of the transistor here is very thick compared to what the source is, what the physical dimension of the source or the drain are. So the gate has no influence whatsoever into the depth of the silicon substrate, and this effectively means that we cannot have control on potential leakage paths that may exist between the source and the drain, and these leakage paths become more and more a problem as we shrink as we know now. So the SOI technology has been introduced to try to tackle this problem, to try to make sure that the gate is in complete control of the piece of silicon that represents effectively the channel of the transistor, and there is no part or no region of this piece of silicon that is not under the direct influence of the gate. So the idea is behind the SOI technology is basically represented by this diagram here. So as you can see, the transistor now is effectively built. The transistor now is effectively this part here only, and is effectively built on a substrate that can be anything, for example silicon, but has on top an oxide. This is called box. This is an insulator, and it's called a box, which stands for buried oxide. So as we can see, the silicon that is used to create source, drain, and body is an extremely thin now part that is exactly on top of this box. Hence silicon over insulator. So the silicon is on top of the oxide. Now this configuration achieves something extraordinary. The idea is obviously extremely simple, but is extraordinary in a way, because now the gate is in full control of the body, and there is no piece of this part of this silicon piece of material that is beyond the reach of the gate. Obviously the silicon substrate is extremely far and is also separated from the rest of the transistor through an insulator, so they are effectively disconnected. And so this means effectively that in this way we can effectively reduce enormously the problem of the gate losing control over the channel when we shrink the transistor. There is also another, we are exploiting here also electrostatic phenomena, and this is that, if you remember, when we one of the big problems when we shrink the transistor is the fact that the depletion areas around the drain and the source contacts extend so much into the channel area that they cause effectively the drain-induced barrier lowering and all the other effects we've discussed. But here, because the body is so confined in space, electrostatic is in a way helping in keeping these depletion regions reduced. You see, when you are creating a depletion region, in this case, if we assume, for example, that the body is p-silicon, what we are doing effectively is pushing away from the drain the holes, and so we create a depletion region here. At the same time, something similar will happen here at the source. But on both sides now we are pushing away the same charge, but both are positive, and so they will repel each other. So there is a force now that is a very simply a Coulombic force now that is contrasting the depletion regions that would like to extend well within the channel area. And so this also is helping, keeping the gate in control of the channel. So this is the fundamental idea behind the use of silicon over insulator technology to ease the process of scaling MOSFET transistors. And so we have single gate SOI MOSFETs like the one that is shown here. This is a single gate, there is only the top gate here, or we may have double gates that I think I can show you. On this slide we are basically saying what we've briefly said previously, and here I can show you the comparison between a single gate and a double gate. So the double gate is represented here and here as well. So this is an example of a single gate, and then the double gates there. Oh, obviously, the use of a double gate is also aimed at further increasing the control of the gate over the channel area. That's the whole point. There are different ways where a double gate there are different ways that someone can use the double gate configuration, and this is what exactly these two graphs here are trying to show. The dot, just so you know, this dot here is indicating where effectively the charge carriers in the channel are moving. So you can see that I can use the double gate in such a way that effectively the charge carriers in the channel move in one localized area, or like in this case, I can use the double gate in a completely symmetric approach in such a way that effectively I'm using two physical locations to let the charge carriers move into the channel when the transistor is on. But anyway, the whole point here is that we use this the SOI technology to increase the control of the gate over the channel, and then from the single gate we go to double gate to also increase further the control over the channel. And here we can see in action the effect of going from single gate to double gate, for example, in these experimental results. So the lines with full symbols are related to a single gate device, and then exactly the same device built with a double gate technology clearly show that the threshold voltage variation due to shrinking. As you can see here, we are plotting the threshold voltage variation as a function of the length of the channels of the transistor. So as we know, as we shrink at a certain point, we will start seeing, because of short channel effects, we will start seeing a deterioration of the threshold voltage. Okay, and that's what these plots, these lines are showing here. So if we compare, for example, the black curve with full symbols and empty symbols, we can clearly see that in the case of the curve with empty symbols, the deterioration of the threshold voltage starts much when the device is already very, very small. So you can see that, let's say, the deterioration starts here when the threshold voltage starts dropping, and we are there at 20 nanometers, while for the black curve in full symbols, the deterioration had already started probably, I don't know, somewhere here at 100 nanometers. So this is exactly showing us practically how important it is to increase the control of the gate over the channel. Please note how thin are these active pieces of silicon over insulator. Here we are talking about 10 nanometers for the green curve, 5 nanometers for the red, and 1.5 nanometer for the black. Oh, it is worth noting here also that by introducing the SOI technology, we immediately were able to create devices with a swing that is effectively the theoretical one for silicon transistors. Here is another example with the same curves that we've seen before. So just another example for you to look at. But what we can see though here is that with double gate soy MOSFET, the best that really we could do before we could start seeing short channel effects effectively is of the order of something like 20 nanometers. So this means that if we want to go even smaller than that, there is no other solution than going 3D. So that's why people are today effectively working on 3D geometries for MOSFET transistors. So in all new devices that you buy today, if there is a MOSFET inside, it will be a 3D geometry, which we've said is either a FinFET or a gate all around. So here you can see which is the idea behind the FinFET. So you have this piece of material of semiconductor that protrudes out of the plane of the substrate, and the gate is surrounding three sides of this fin. Still, you see that we are talking always of a technology that is based on the soy technology. So soy technology has come to stay. So it is still there. And on this slide, you can actually appreciate a real now FinFET. This is an Intel 22 nanometer technology FinFET. So it's extremely amazing what they managed to do there. And just please note how thin is the fin at the half height. And note also that in this particular device they are using a metallic gate. Oh, remember that probably in the long channel traditional standard transistor, MOSFET transistor, there were no metals. Any component that had to have metallic properties was actually made with polysilicon. So a form of silicon that is effectively behaving like a metal. So, but today metals have actually entered very well the factories, semiconductor factories. So as you can see here, they're using a metal gate, and also there is a high K. So HK stands for high K. And here now is the other 3D geometry that we may come across, that is the gate all around. So here in this case the gate is actually embracing the piece of silicon where the channel is and the source and the drain. So as you can see here, there is either a planar, a horizontal configuration, or a more probably in fashion, I would say, vertical one that is made like that. And so the gate all around approach is particularly prone to exploit the use of nanowires. And that's what I'm trying to show you here in this next couple of slides. So the presence of a nanowire, especially in the vertical or also in the horizontal actually geometry, allows people to actually use multiple gates on the same piece of silicon. So this is obviously enormously important for high integration. Okay, so when you want to put many devices, even more devices, into the same spot. And here you can see a typical case of a real now gate-all-around with a silicon nanowire. Obviously, the silicon nanowire is this one here, and the gate is all around. So remember that this is effectively the gate stack, if you like. So there is a metal, and somewhere here there must be also an insulator. Okay, and underneath is the channel that we are controlling with the gate. And this is also, a very nice a practical example of a working gate-all-around transistor. You can see here that you can, with a vertical approach, you can achieve huge integration capabilities with this type of devices. So you can fit many into a very small space. And this is actually an example where the semiconductor has been replaced with a 3-5 semiconductor. So it's not silicon, but is, as you can see, indium, gallium arsenide, or some of these alloys. And again, you can see that you can achieve extremely good swings, and also here they are explicitly telling us the DIBL effect that you could expect on this type of devices. So they are telling us, you remember the DIBL is the drain-induced barrier lowering. That is, if you remember, if you apply voltage on the drain, you should expect that as a short channel effect, you should expect that there is some effect on the height of the barrier. So this number here is telling you that for each volt you apply on the drain, you should expect a lowering of the barrier in the channel by 35 millivolt. So it's a very small effect, but it's quite remarkable that they are also telling you that. So in a way, if you like, in this device, the DIBL effect is effectively negligible, but still measurable, as you can see. So you can understand from these things that I'm telling you that short channel effects are always there, and people keep fighting with these short channel effects every day, trying to keep them at bay. Every time that a new step in the scaling process is made, more and more techniques must be invented, if you like, in order to overcome the short channel effects. And here we see how the gate-all-around is actually en route to be the transistor of the next maybe 15 years or so. So as you can see, the planar saw is expected to have as a limit, you can see here 14 nanometers, the FinFET probably 10 nanometers. Well, the gate-all-around is expected to have its physical limit at effectively 5 to 8 nanometers. Okay, so for maybe the next few years, we will still be relying on probably gate-all-around and FinFET a little bit, and then we will see. We shall see in a moment. Remember, since we are talking about gate-all-around, remember that because gate-all-around is based on effectively a nanowire, we've discussed some time ago nanowires. In chapter 3, we've seen that when we are talking about 1D confined structures, then we realized, if you remember, go back to chapter 3, that the dispersion relation is effectively something like this one. And there is effectively the dispersion relation EK is made of many parabolic modes, and each one accessible and related to a different, if you remember, quantum number. Gate-all-around devices are also performing very, very well compared to other existing technologies. And this is what effectively this plot is showing us. So on this plot, we show the current when the device is on, where, as compared to versus the current when the device is off. So obviously we want, if you remember well, what we want in a transistor is when it's on to conduct as much current, as more current as possible, and when it's off to be off, so the current to be as small as possible. So really on this plot we would like to stay in this quadrant, in this area, so on the bottom right corner as much as possible. So as you can see, the technology has been, the steps that the technology has been doing in the last 20-30 years are exactly going in that direction. So with the standard transistors, we were here, and double gate up here with the blue dots. SOI technology, obviously more the single gate or double gate here, but you can see that the nanowires are really down here, and when the diameter is 10 nanometers, we get these points. But as we move to 3 nanometers, we are actually moving the right direction, and we are moving toward the right spot. So really, we are creating fantastic devices if we compare, the different technologies. Oh, this is just to, it relates to what we've already said, that when you deal with nanowires, the dispersion relation effectively is made of several parabolas, each one corresponding to a different quantum number. So this is a practical example of a specific situation, which is a 3 nanometer by 3 nanometer silicon nanowire. Okay, now just to conclude this exploration of nanoscale transistors, nanoscale MOSFET transistor, sorry, we should try to remember what we've seen in chapter 3 when we were discussing 1D confinement, when we were discussing the nanowire. And in that situation, we not only discussed the dispersion relation and where the energy levels are and so on and so forth, but we also had a look at the wave function. So where physically the electrons are. So and there is a result that I'm going to recall to remind you now. So let us imagine that we are dealing with a nanowire that, if we look in cross-section, is made like that. So this is my silicon nanowire. It's a square, imagine, nanowire in cross-section. We have the silicon dioxide around, our insulator, and the gate. So this is a typical gate-all-around device. When this silicon nanowire is very large, quite big, so like imagine 20 nanometers by 20 nanometers, this is still effectively quite a big nanowire, and so we should expect that the electrons will travel within the nanowire, but if they are still effectively classical electrons, they will tend to repel each other. And so we could expect that they travel as far as they can from each other. So they would be traveling in these corners when the transistor is on. And this is what this plot here is showing you. So this is the density of electrons in the channel. So you can see that there is one spot, one high density at one corner, at the other corner, and so at the four corners. So it is very interesting now to see how this is obviously a simulation, but is obviously the one that represents what is exactly happening. As you move to smaller and smaller nanowires, what eventually happens is that the electrons, I will draw this in red, travel just at the center of the nanowire. If you remember, the eigenfunction of the fundamental, the ground state of our 1D nanowire, if you go back to chapter 3, had exactly this feature. The highest probability of finding an electron was exactly in the middle, and that's what this result here is showing you. So in the future devices, gate-all-around devices that are in the size of really few nanometers, the electrons travel very close to each other in the middle. So this is quite a remarkable result. That electron in the quantum situation will like to actually stick together and travel in the middle of the silicon nanowire. So this is quite a nice result that I wanted to point out to you. And in the next few slides, we will have a look at what could be after all these evolutions of the MOSFET device. So which other ideas are there to further scale the transistor concept? The first one we will look at is the tunnel transistor. The geometry is the one that is shown here. So it still reminds a lot, obviously, our MOSFET transistor, but this time we are going to rely on tunneling. And as you can see, the basic structure is made of a piece of semiconductor. One side is, for example, P, and the other side is, for example, N. And in between there is the channel area is slightly doped, or also could be intrinsic. You can see still there is obviously a gate stack on top, and the idea reminds really a lot what we've seen for the tunnel diode. So these energy diagrams here are there exactly to show you the principle. And so as you can see, VG here is used to actually act on the energy diagram of the channel and move it up or down, and VD instead moves up or down the energy diagram corresponding to the semiconductor in the drain. So you can imagine that if we have a small VDS bias and we now start applying a positive VGS in this diagram, we will push the channel area down enough for tunneling at a certain point to happen between the P side and the channel area. So this is exactly the same process that we have seen, if you remember, in the tunnel diode. So this is a type of transistor that relies on tunneling between the source contact in this case and the channel. Obviously, as we've probably already understood here, doping and material choice is extremely important to have this desired band behavior. Just a few more details about the tunnel transistor. Obviously, as any other field effect device, the tunnel transistor relies on the fact that the gate has to have good control over the channel. And so also here we have single gate devices like the one we've just seen. As you can see here, I'm highlighting the fact that this is an intrinsic piece of material, so we said either slightly doped or intrinsic is fine, and we can have also double gate devices or gate all around devices. They all aim at increasing the control of the gate over the channel area, but they are all tunneling devices. And because the control of the gate is in this case also extremely important, we can see in this plot that this is exactly highlighted by the fact that if the channel, the thickness of the piece of semiconductor, the thickness of this layer here is not small enough, and small enough means 2 nanometers, for example, then we may effectively lose the transistor behavior. As you can see, when you are at a thickness of already 10 nanometers, there is basically very little trans characteristic there. Okay, so please note that this what we're plotting here is actually the trans characteristic. You see, is the current in the channel versus the VG. And as you can see, when the body of the, if you like, of this tunnel transistor is 2 nanometers, in this case we achieve even the theoretical swing of 60 millivolt per decade. And similar very good results are obtained when we go from single gate to double gate and gate all around. So as you can see, the swing improves, and actually here we can even go beyond the theoretical limit. And this is actually the key point in the tunnel transistor, that because it is based on tunneling, it can actually achieve a swings that are better than the theoretical limit we've mentioned now several times, valid for the standard field effect transistor. Another very interesting approach is the one of tunnel transistor based on a Schottky barrier. Here the idea is also tunneling, but this time we don't use semiconductors anymore effectively. Only the semiconductors are only used in the channel, but now we use metals in the source and in the drain. And as we know, the metal semiconductor contact creates a Schottky barrier. If you remember, the Schottky barrier is effectively related to the band bending happening into the semiconductor. So this is the metal and this is the semiconductor. And so in this case, when we act on the gate, what we do effectively, we accumulate some charges, or we repel some charges from the top interface of the semiconductor with the gate insulator. And so this presence of charge in that very important area, what it does is, as we know now, creates a bending of the locally of the energy diagram. So when we could imagine that when Vg has, for example, a positive value, the bending in the semiconductor is made in this way, and so the electrons now see a very big barrier in front of them, so they cannot effectively move. While when we apply, for example, a Vg that is the opposite sign, then we effectively bend downward this time, and so now the electrons can happily tunnel through. And so that's the idea behind the tunnel transistor based on a Schottky barrier. On this slide, you can actually see some results of a practical device. So I'm not going to spend too much time on this. It's just for you to, I thought it was nice for you to have a look, for example, at this image of how tiny are these devices and how also delicate in a way are this type of structures. So extremely small. You can see here, the features are enormously small, and it's actually, quite an achievement that, these devices operate so well. The last example I wanted to discuss with you is regarding nanoscale transistors, is the single electron transistor. So we've already come across some time ago in chapter 3, I think, the single electron tunneling junction. So we are in a way familiar now on how we can make a single electron device. But here now we want to make a transistor. So what we need to do is we need to have some tunneling barriers. As you can see here, there are these two, one on the source, one on the drain. In the middle we have some quantum particle, 0D confined structure, an island, a nanoparticle, something. And then we need a gate. So we need a gate to be able to change the potential of the channel, in this case our nano object, our 0D confined structure. So we can imagine, for example, to have this type of transistor here. We have our source, drain, and gate, some tunneling barriers, in this case could be vacuum between the source and the molecule, and the drain and the molecule, and then we have our gate. So as we've seen in chapter 3, 0D confined structure will have some quantized states located in a certain point in energy. And effectively, if we were to try and operate this type of device, here we imagine that we put some nanoparticle here. I think this is a C60, a C60 particle. So if we imagine that, for example, the state, the first available state in this 0D confined structure is extremely well defined in energy. So we can say this by highlighting here the width, let's say, of the state, this gamma factor here. So you can see it's 10 micro EV, so extremely sharp state, let's say. And if we try now to apply some VDS across the source and drain, and we apply some voltage to the gate, we realize that the trans characteristic looks like that. So it's a very special trans characteristic. As you can see, the current is normally 0 up to a certain point, then is non-zero for a tiny window, and then becomes 0 again. So it's quite different, this trans characteristic, from the one that we've seen for our standard transistor. But still, we can use this to operate this device as effectively as a transistor. And we can see how it operates better here now. So this slide is showing you now two situations. A situation where the state in our 0D confined structure is very sharp in energy, while another situation where it's much broader. So you can see that in the blue case, it's 10 milli EV, the width, let's say, of my state. And in that case, we would expect this type of blue curve for the trans characteristics. So we will discuss both cases just to have a better idea of how these things can work. please note that these trans characteristics have been obtained assuming that VDS is small. Okay, and that's something we need to keep in mind in the next few slides. So in the case of a very sharp state, as the one that you see is depicted here, so very well localized in energy, then what happens is that when VG is like 5 volts, so if we have a look back here when in the case of the sharp very localized state, when VG is 5 volt, we are down here, so we are far from the region where the transistor becomes on. So the reason it's not on is because, as you can see, the state is above both the Fermi level of the source and the drain, and so when VDS is small, there is no available state for the electrons here to move to. The state in the molecule is slightly higher, and so the states are not available, so this electron here cannot move effectively. And so there is a conductance gap. Or the reason then this is now the output characteristic, as you can see, is IDS versus VDS for VGS 5 volts. So the reason then at a certain point, though, if we increase too much VDS, the current could actually turn on the transistor, is because if we look at the schematic of this peculiar device, this is all based on electrostatic coupling. So if we increase too much the drain voltage, this actually is able to affect a little bit also the potential of the particle. So the potential of the particle is not anymore due only by the gate, controlled by the gate, but is also a little bit affected by the potential in the drain. And this, how much this, how well the potential of the particle is controlled just by the gate and not by the drain, it all comes down to the values of these capacitances here. So you can see that the capacitance on the gate here is 1 attofarad, while this one is 10 attofarad. So going back to why the current at a certain point could eventually, if VDS is too big, start flowing in this device, because if we push this too much down, then this also is dragged a little bit down as well. And then it could then align with the source, and so some current could start flowing. But we are not interested in too much in these scenarios. We are interested in the case of VDS small. Okay, so for VGS 5 volt and VDS small, there is no current flowing through the device. When we do increase a little bit of VGS, and we now are at a value of VGS that effectively aligns with the moment when the transistor should be on, then what is effectively happening is that we are placing the state between the Fermi level of the source and the Fermi level of the drain. So now some electrons can tunnel and tunnel out. And so in this case, current is flowing, as you can see. For a small VDS, we will always have some current flowing through the device. If we keep increasing VGS, we push the state so down that effectively goes beyond the lowest of the two Fermi levels. And so even if I was able to place an electron there, then this electron wouldn't be able to effectively come out on the other side. And so that's why in this case there would be no current. In the case that the state instead is broader in terms of energy, then we have more smooth behavior. So all these curves we've seen up until now becomes more smooth. And so you can have a look through this slide and see that effectively they remind a lot what we just seen. Simply the curves are a bit more soft in a way. It is based on what we've just said in this couple of slides. We've understood something very important, that in the operation of our single electron transistor, both the gate voltage and the source or drain voltage play both a very important role. And to better understand this, we generally, people working on single electron transistor generally refer to this type of plot that shows where the transistor conducts current, which are these colored areas here, and where the transistor doesn't conduct current, which are these white areas here, in a plot where we are actually showing VG values and VS values. So it is very interesting here to try and understand why on this plot these features appear, these like rectangles or even squares appear. In order to understand that, let us first start from this point here at 0, 0, in this hypothetical case, where we should imagine that the energy diagram of our single electron transistor should be something like this. So this is the Fermi level of the source, the Fermi level of the drain, and this is the first state in our 0D confined structure. Then there would be a second state here, and so on and so forth. So we can imagine that the first state is not aligned, of course, with the Fermi level, will be slightly above it. If we then move along the VG axis, so if we start applying some positive VG, we effectively push downward our states in the 0D confined structure. And so until we reach this point here, where what happens is effectively what is shown in this diagram. So we align the state with either the drain or the source. On this plot, we are assuming that the drain has a fixed potential and we are applying the potential on the source, but it's exactly the same. This device is completely symmetric anyway. So we are now at this point. So if we now imagine now to move along this line, for example, what we are effectively doing is we are increasing slightly VG, but we are also increasing slightly VS. So when we reach this point here, the bad diagram should look like this one here. So we've increased slightly VS, so we pushed down compared to the drain the source, but at the same time we've pushed a little bit down also the 0D confined structure states, and effectively in a way to maintain it aligned with the source. So this is effectively what this line here represents, is the line generated by effectively, if we move along this line, we keep the first state aligned with the source. Something similar we can be said for this line here. When we move along this line here, we are effectively maintaining the first state aligned with the drain in this case. And we can see that if we look at this point here, indeed we have the first state aligned with the drain. And so we can visualize this in this way here. So these two lines correspond to the first state aligned either with the source or either with the drain. for fun, look at the other diagrams here that correspond at the other points, shown on this diagram. But this is the main thing. So these lines are generated because of this electrostatic effect that VG and VS play on the entire device. So they align. If we move along this line, we are effectively aligning the states in the 0D confined structure either to the source or to the drain. And so we can now obviously guess correctly that if we now look at this line, for example, this line corresponds to the second state being aligned to the drain. And this other line here corresponds effectively to the second state aligned to the source. And just to understand what happens at the intersections, if we look at this intersection here we have the intersection between this green line, that is the first state aligned to the D, to the drain's contact, while the red line is the second state aligned to the source. And so in this point here, the energy diagram of the device should be something like this. In this point, we have the second state aligned to the source and the first state aligned to the drain. Okay, so this effectively concludes our exploration of transistors, scaling challenges, and what people are doing in order to create nanoscale transistors. So thank you for listening, and I'll see you next time. Bye.